and a great day in the sense 37th annual month-long science festival. 37 years annual month-long science festival. About the science form was started by the great legendary figure Dr. Narasimha in 1962 with a clear-cut objective of popularizing science, nothing else. Maybe on that day, one or two students, I was student, H.R. Ramakrishna was student, and Narasimha was a teacher, lecturer, and we all decided to start like that, one lecture on Wednesday. And they used to tell myself and Ramakrishna, chelas of Dr. Narasimha, other colleagues used to say to Narasimha, but just imagine, 62 Wednesday, one Wednesday we start, and you are 2014, not even a single Wednesday has been let off, such beautiful lectures. And like that, we are on 2578, the 2578 lecture. On such an occasion, very, very distinguished Prof.Roddam Narasimha is here, and on behalf of you and on behalf of the Bangalore Science Forum, I extend him a very warm welcome. And there are young people here, MSc Mathematics and other students. Having them in the mind, he is presently a DST Year of Science Professor at Jawaralal Nehru Center for Advanced Research, Scientific Research. He was educated at the University College of Engineering, then was very, very important college, and at the Institute of Science, even today is very important, and obtained his PhD at the California Institute of Technology. Caltech PhD ಅಂದ್ರೆ ನಾವೇನು ಯೋಚನೆ ಮಾಡಬೇಕಾಗಿಲ್ಲ ಅಂತ ನೋಡಬೇಕು ದರ್ಶನ ಮಾಡಬೇಕು ಅನ್ಸುತ್ತೆ actually. He's here, the students know that Caltech is coming from one of the most prestigious institutions of USA. In 1961, he joined the Institute of Science in 1962 and was associated with the Department of Aerospace Engineering in various capacities from that date till 1999. ನಾನು ಸ್ಟೂಡೆಂಟ್ ಆಗಿದೆ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ನಲ್ಲಿ ನಮಗೆ ತುಂಬಾ ಇಷ್ಟ ನೋಡಿದೆ ಸೈಕಲ್ ಮೇಲೆ ಒಬ್ಬರು ಮಧ್ಯ ನಿಲ್ಸ್ಕೊಂಡು ಮಾತಾಡ್ತಾರೆ such a great day, And in 1982, he founded the Center for Atmospheric Sciences, now Center for Atmospheric and Oceanic Sciences, which he headed till 1989. During 84 to 93, he was director of the National Aerospace Laboratories. For many years, since 1982, he held a visiting position at Caltech as Clark B. Millikan Professor or Sherman Fairchild Distinguished Scholar. During 1989-90, he was Jawaralal Nehru Professor of Engineering at Cambridge University in England. He has also held visiting positions at NASA, Langley, Strattel, University of Brussels, Adelaide University from 19 to 94. He was INSA Golden Jubilee Research Professor, and from 94 to 99, the ISRO K.R. Ramanathan Distinguished Professor at Institute of Science and JMPSR. He was Director of the National Institute of Advanced Studies during 97-2004. ಇವತ್ತು ಸೈಂಟಿಫಿಕ್ ಅಚೀವ್ಮೆಂಟ್ಸ್ ಎಷ್ಟೊಂದಿದೆ ಅಂತ ಹೇಳಿದ್ರೆ ತುಂಬಾ ಇಲ್ಲ ಸೈಲ ಏನಿಲ್ಲ ನಾನು ಯಾಕೆ ಹೇಳ್ತಾ ಇದೆ ಅಂತ ಹೇಳಿದ್ರೆ ಇದು ನೋಡಿದಾಗ ಗೊತ್ತಾಗಲ್ಲ ಬಟ್ IT ಬಂದಿದೆ ಇನ್ಫಾರ್ಮೇಶನ್ ಟೆಕ್ನಾಲಜಿ ಅದೇ ದುಡ್ಡು ಸಿಕ್ಕಾಬಟ್ಟೆ ಹೆವಿ ಸ್ಯಾಲರಿ ಅಂಡ್ ಅದರ್ ಥಿಂಗ್ಸ್ ಅಷ್ಟು ಪ್ರಾಫಿಟ್ ಆಯ್ತು ಇಷ್ಟು ಪ್ರಾಫಿಟ್ ಆಯ್ತಲ್ಲ ಆ ಗಲಾಟೆ ಸೈನ್ಸೇ ಮಾಡ್ತಾರೆ ನಾವು ಆಕ್ಚುಲಾಗಿ ಟುಡೇ ಅನ್ಫಾರ್ಚುನೇಟ್ಲಿ ನೋಬಡಿ ಇಸ್ ಟೇಕಿಂಗ್ ಸೈನ್ಸ್ ಇನ್ ಕಾಲೇಜಸ್ ಲೈಕ್ ನ್ಯಾಷನಲ್ ಕಾಲೇಜ್ ಬಸವನಗುಡಿ ಆಲ್ಸೋ ಫಿಸಿಕ್ಸ್ ಇವ್ರ ಕಾಲದಲ್ಲಿ 200 ಜನ ಆಯ್ತು ಸೀಟ್ ಸಿಗ್ತಾ ಇಲ್ಲ 20 ಜನ ಮಾಡೋದಿಲ್ಲ ಆಕ್ಚುಲಾಗಿ ಇದು ಎಂತ ಬಯೋಡೇಟಾ ಅಂದ್ರೆ ದಿಸ್ ಪ್ರಿಂಟೆಡ್ ಅಂಡ್ ಕೆಪ್ಟ್ ವಿತ್ ಎವರಿ ಸ್ಟೂಡೆಂಟ್ ದಿಸ್ ಇಸ್ ಐ ಓಪನರ್ ಫಾರ್ ದಮ್. Professor Narasimha's research has been chiefly concerned with aerospace and atmospheric fluid dynamics. He is internationally known for his extensive studies of transition between laminar and turbulent flow, the structure of shock waves, various characteristics of fully developed turbulent flow, the fluid dynamics of clouds, near surface temperature distributions, and eddy fluxes in tropical atmospheric boundary layers. His recent laboratory studies on cloud flows carried out with colleagues and students have been called amazing, resulting in groundbreaking research on important scientific problems relevant to global climate change and the Indian monsoons. He has been closely associated with aerospace technology development in India at both technical and policy making levels. During 77-79, he was the chief project coordinator in Hindustan Aeronautics Limited and led a joint HAL-NAL-IS Institute of Science team carrying out early conceptual studies of the LCA. As director of NAL, he initiated and oversaw several major technology programs, including the development of carbon composite wings and flight control systems for the LCA. Our science form lecture actually. Under his leadership, NAL made the first parallel computer in the country in 1986 and fabricated and flew the first fiberglass aircraft in the country. He served on the board of directors of Hindustan Aeronautics Limited for several years. As a member of Prime Minister Rajiv Gandhi's Scientific Advisory Council, you are instrumental in establishing a major parallel computing initiative in the country. You are president of the Indian Academy of Sciences during 92 to 94 and spearheaded a new program on university education science, leading to the establishment of the journal Resonance and other academic programs involving teachers and students. He has served 3 terms on the National Security Advisory Board. Currently is a member of the Scientific Advisory Council to the Prime Minister. He has been a member of the Space Commission since 1989. He led conceptual studies of the Indo-French atmosphere research satellite megatropics and continues to be co-chairman of the Joint Scientific Working Group of the satellites. In fact, the upcoming satellites in Dr. Shivakumar lecture total. As director of NIAS, Professor Narasimha initiated a series of major dialogues on the international security issues with the US National Academy of Sciences and other bodies, and pursued his interest in history of science and technology and philosophy underlying Indic rationalism. Ivar start agirthe lecture ide total age. Idella nodta anisate uduguru bada important total age. Of course, he got his BE in mechanical engineering first class from University of Mysore. Adu particular yakiರ್ತದೆ ಅಂದ್ರೆ ಬೇಕಾದಷ್ಟು ಆನರ್ಸ್ our first honors for ಹಾಕಿರೋದು ಶಾರದಾಂಬಾ ಪ್ರೈಸ್ ಯೂನಿವರ್ಸಿಟಿ ಆಫ್ ಮೈಸೂರು. the first in 1950 for a student our channel understand just encourage ಮಾಡ್ತಾ ಇರ್ತಾರೆ. Then diploma in aeronautical engineering due to science first rank then, and PhD in aeronautics and physics California Institute of Technology. ಅಂತೂ ನಮ್ಗೆ ಸಿಕ್ಕೋದೇ ಕಷ್ಟ. And of course they have got several awards. ನಮ್ಮ ಕರ್ನಾಟಕ ಪಾಯಿಂಟ್ ಕರ್ನಾಟಕ ರಾಜ್ಯೋತ್ಸವ ಅವಾರ್ಡ್, ಇಂಡಿಯನ್ ಗವರ್ಮೆಂಟ್ ಪದ್ಮಭೂಷಣ್ ಅವಾರ್ಡ್, ಅಥವಾ ಅಮೆರಿಕನ್ ಸ್ಟ್ಯಾಂಡ್ to a fellow American Institute of Astronautics and Aeronautics. ಬೇಕಾದಷ್ಟಿದೆ, ಕೆಲವು ಮಾತ್ರ ಮೆನ್ಷನ್ ಆಗ್ತಾನೆ. Of course, ಪದ್ಮಭೂಷಣ್ ಅವಾರ್ಡ್ ಸೈನ್ಸ್ ಅಂಡ್ ಇಂಜಿನಿಯರಿಂಗ್, ಲೈಫ್ ಟೈಮ್ ಎಕ್ಸಲೆನ್ಸ್ ಅವಾರ್ಡ್ ಇನ್ ದ ಸ್ಪಿಯರ್ ಆಫ್ ಅರ್ತ್ ಸಿಸ್ಟಮ್ಸ್. ನನಗೆ ಅನ್ಸುತ್ತೆ ಇನ್ನು ಭಾರತ ರತ್ನ ಒಂದೇ ಅಂದ್ರೆ ಹುಡುಕೊಂತದೆ. ಲೆಟ್ ಮಿ ವಿಶ್ ಹಿಮ್ ದಟ್ ದಿ ಕಂಟ್ರಿ ಕನ್ಫರ್ಮ್ಸ್ ಅಪಾನ್ ಹಿಮ್ ದಿ ಭಾರತ. There are so many professional affiliations, and in fact ನನಗೆ ನೋಡ್ತಾ ಇದ್ದಾಗ ಅನ್ಸುತ್ತೆ ಇದ್ರ ಬಗ್ಗೆ ನಾವೆಲ್ಲ ಚಿಂತನೆ ಮಾಡೋಕಂದ್ರೆ ಇಂಥದ್ದು ಒಂದು ಲೈಫ್ ಟೈಮ್ ಮಾಡಕ್ಕಾಗತ್ತ. ಜವಾಹರ್ಲಾಲ್ ನೆಹರು ಪ್ರೊಫೆಸರ್, ಕೇಂಬ್ರಿಡ್ಜ್ ಯೂನಿವರ್ಸಿಟಿ, ಕ್ಲಾರ್ಕ್ ವಿಲ್ಕನ್ ಡಿಸ್ಟಿಂಗ್ ಪ್ರೊಫೆಸರ್, ಇದೆಲ್ಲ ತುಂಬಾ ಸಂತೋಷ ಆಗುತ್ತೆ. ಅಂತ ಡಿಸ್ಟಿಂಗ್ವಿಶ್ ಪರ್ಸನ್ ಇವತ್ತಿನ ಬಂದಿದ್ದಾರೆ. ನೀವೇ ನನಗೆ ಸಾಮಾನ್ಯ ನಾನು ವೆಲ್ಕಮ್ ಸ್ಪೀಚ್ ಹೇಗೆ ಮಾಡ್ತೀನಿ ಅಂತ ಹೇಳಿದ್ರೆ ಫುಲ್ ಹಾಲ್ ಫಿಲಪ್ ಆಗೋತಂಗ ಮಾಡ್ತಾ ಇರ್ತೀನಿ. ಇವತ್ತು ಆಗಿಲ್ಲ ಹಾಲ್ ಫಿಲಪ್ ಹಾಕೊಟ್ಟಿದೆ, ನೆಕ್ಸ್ಟ್ ಬಂದು ನಿಂತ್ಕೋಬೇಕಾಗತ್ತೆ. ಒಂದೇ ಒಂದು ಹೇಳ್ಬಿಟ್ಟು ಏನ್ ಮಾಡ್ತೀನಿ, ಎ ಫ್ಯೂ days back, maybe 2 weeks back or 3 weeks back, Professor Ian Lipkin, who had done a lot of work in what's called genome, he was here. ಅವರು ನೋಡಿದ ತಕ್ಷಣ ಸುಮ್ಮನೆ ಕೊಟ್ಟೆನೋ ಕೇಳಿದವ ನೋಡ್ಬಿಟ್ಟ ತಕ್ಷಣ ಹೌ ಮಚ್ ಆಫ್ ಮನಿ ಸ್ಪೆಂಡ್ ಆನ್ ದಿಸ್ ಅಂತ. ನಾನು ಹೇಳಿದೆ ನಾಟ್ ಇವನ್ ಸಿಂಗಲ್ ಪೈಸಾ ಅಂತ. ಇವಾಗ ಜಾಸ್ತಿ ಟೇಕನ್ ಬ್ಯಾಕ್ ಕಂಪ್ಲೀಟ್ಲಿ. ಒಂದು ಪೈಸಾನು ಖರ್ಚು ಮಾಡಿಲ್ಲ. 2578 ಇಫ್ ಅಟ್ ಆಲ್ ಇವನ್ 1/2 ಕಾಫಿ, ನಥಿಂಗ್ ಎಲ್ಸ್. ಆಮೇಲೆ ನಾನು ಸುಮ್ಮನೆ ನಾನು ಐ ಎಮ್ ವೆರಿ ಸ್ಮಾಲ್ ಮ್ಯಾನೇಜ್ಮೆಂಟ್ ಆಫ್ ಹಿಮ್. ನೋಬೆಲ್ ಪ್ರೈಸ್ ಅಂತ ನಾಲ್ಕು ಮಾಡ್ತಾರೋ ಪರ್ಸನ್ಸ್. ಯು ಆರ್ ಟ್ರಾವೆಲ್ ವರ್ಲ್ಡ್ ವೈಡ್, ಯು ಆರ್ ಇನ್ ಬ್ರಿಟಿಷ್ ಕೊಲಂಬಿಯಾ, ಯು ನೋ ಹಾರ್ವರ್ಡ್, ಯು ನೋ ಕ್ಯಾಲ್ಟೆಕ್. ಬೈ ಚಾನ್ಸ್ ಹ್ಯಾವ್ ಯು ಸೀನ್ ಎನಿವೇರ್ ಒನ್ ಸಚ್ ಪ್ರೋಗ್ರಾಮ್ ಅಂತ ಕೇಳಿದೆ. ಸರ್ಟನ್ಲಿ ನಾಟ್ ಅಂತ ಹೇಳಿದ ತಕ್ಷಣ ಎರಡು ಕಾಂಪ್ಲಿಮೆಂಟ್ಸ್ ಡಾಕ್ಟರ್ ನರಸಿಂಹನವರಿಗೆ, ಬ್ಯಾಂಗ್ಳೂರ್ ಸೈನ್ಸ್ ಮಾಮ್ಗೆ, ಅಂಡ್ ಅಪಾರ್ಟ್ ಫ್ರಮ್ ಇಟ್ ನಿಮಗೆ ಕಾಂಪ್ಲಿಮೆಂಟ್ಸ್. ಯಾಕೆ ಹೇಳಿದ್ರೆ ಎಷ್ಟೊಂದು ಜನ ಬಂದಿರಲ್ಲ ಫಸ್ಟ್ ಡೇ ಎಲ್ಲ. ನೀವು ಬೈ ಚಾನ್ಸ್ ನಾಳೆಯಿಂದ ಇನ್ನೊಬ್ಬನ ಕರ್ಕೊಂಬರಕ್ಕೆ ಗಂಡ ಹೆಂಡತಿನೋ ಹೆಂಡತಿ ಗಂಡನೋ ಅದು ಮಕ್ಕಳನ್ನ ಕರ್ಕೊಂಬರ ಜಾಗರೇ ಅಲ್ಲ ಪುಸ್ತಕ. ಅಂಡ್ ಈಚ್ ಲೆಕ್ಚರ್ ಇಸ್ ಬ್ಯೂಟಿಫುಲ್. ಸುಮ್ಮನೆ ಹೇಳ್ತೀನಿ, ಸಿಂಥೆಟಿಕ್ ಬಯಾಲಜಿ ಎಂತ ಲೆಕ್ಚರು, ಹ್ಯೂಮನ್ ಬ್ರೈನ್, ವಾಟ್ ವಿ ನೋ ಅಂಡ್ ಚಾಲೆಂಜಸ್ ಅಹೆಡ್, ವಂಡರ್ಫುಲ್ ಲೆಕ್ಚರ್ಸ್. ಫಿಸಿಕ್ಸ್ ಆಫ್ ಗ್ಲೋಬಲ್ ವಾರ್ಮಿಂಗ್ ನೋಡಿ ಒಬ್ರು ಹೇಳಿದ್ದಾರೆ, ಡಾಕ್ಟರ್ ಜಗನ್ನಾಥ್ ನಮ್ಮ ಸ್ಟೂಡೆಂಟ್ ಆಗಿದ್ದರು ಅಂಡ್ ಲೇಟ್ ಆನ್ ಯೂನಿವರ್ಸಿಟಿ ಪ್ರೊಫೆಸರ್. ಬ್ಯೂಟಿ ಇಸ್ ದಿ ಮಿಡ್ಲ್ ನೇಮ್ ಆಫ್ ಕ್ಲಾಸ್. ಬ್ಯೂಟಿ ಇಸ್ ದಿ ಮಿಡ್ಲ್ ನೇಮ್ ಆಫ್ ಕ್ಲಾಸ್. ನನಗೆ ಇನ್ನೂ ಅರ್ಥ ಆಗಿಲ್ಲ. ಅವ್ರೆ ಎಷ್ಟು ಬ್ಯೂಟಿಫುಲ್ ಇರ್ತದೆ. ಹಾಗೆ ನೋಡ್ಕೊಂಡ್ಬರ್ತಾರೆ. ಸೆಕ್ಯೂರ್ ಡೇಟಾ ಪ್ರೋಸೆಸಿಂಗ್ ಇನ್ ದಿ ಕ್ಲೌಡ್. ಇಲ್ಲೊಬ್ರು ಕ್ಲೌಡ್ ಕಂಪ್ಯೂಟರ್ ಲೆಕ್ಚರ್ ಕೊಟ್ಟರು. ಕೊನೆಯಲ್ಲಿ ಹೇಳಿದ್ರೆ ಯಾರಿಗೂ ವಿಚಾರ ಸರಿಯಾಗಿ ಗೊತ್ತಿಲ್ಲ, ಬಟ್ ಇಟ್ ವರ್ಕ್ಸ್ ಸ್ಟಿಲ್ ಈವನ್ ಟುಡೇ ಇಸ್ ವರ್ಕಿಂಗ್, ಇಟ್ ವಿಲ್ ವರ್ಕ್ ಟುಮಾರೋ. ಪ್ರೊಫೆಸರ್ ದಿನೇಶ್ ಅಂತಾರೆ, ವಂಡರ್ಫುಲ್ ಲೆಕ್ಚರ್ ಆಕ್ಚುಲಿ. ಅಂಡ್ ಎವಲ್ಯೂಷನ್ ಆಫ್ ಸೈನ್ಸ್, ನ್ಯಾನೋ ಎಲೆಕ್ಟ್ರಾನಿಕ್ಸ್, ಮಸ್ಕಿಟೋಸ್ ಅಂಡ್ ಡಿಸೀಸಸ್. ಕೊನೆ ಕನ್ನಡದಲ್ಲಿ ಮಕ್ಕಳ ಬೆಳವಣಿಗೆ ವಿಕಾಸ, ಅದರಲ್ಲಿ ಕಂಡು ಬರುವ ತೊಂದರೆಗಳು, ಅದು ಇದೆ ಆಕ್ಚುಲಿ. ಆಮೇಲೆ ಈ ಗಲಾಟೆಯಲ್ಲಿ ವಿಜಯಲಕ್ಷ್ಮಿ ಬಾಳಿಕ್ ಅಂದ್ರೆ ಬಹಳ ಪಾಪ್ಯುಲರ್ ಪರ್ಸನ್ ಸಿಕ್ಬಿಟ್ಟಿದ್ರು. ನಾನು ಹೇಳಿದೆ, ಮೇಡಮ್ ಒಂದು ತಿಂಗಳಿಂದ ಫೋನ್ ಮಾಡ್ತಾ ನೀವು ಸಿಕ್ಲಿಲ್ಲ ಅಂತ. ಅವ್ರಿಂದ ಲಂಡನ್ ಹೋಗಿದ್ದೆ, ನೆನ್ನೆ ತನಕ ಬಂದೆ ಅಂತ ಹೇಳಿದ್ರು. ಎಷ್ಟು ನಮ್ಮ ಕಂಡ್ರೆ ವಿಶ್ವಾಸ ಅಂದ್ರೆ ಬೈ ಚಾನ್ಸ್ ಯಾರ ಸ್ಪೀಕರ್ ತೊಂದರೆ ಆದರೆ ಆ ಸಮಯದಲ್ಲಿ 1 hour ನೋಟಿಸ್ ಕೊಡಿ, ನಾನು ಬಂದು ಮಾತಾಡಿ. ಎಕ್ಸಲೆಂಟ್ ಸ್ಪೀಕರ್ ಡಾಕ್ಟರ್ ವಿಜಯಲಕ್ಷ್ಮಿ ಬಾಳಿಕು ಅಂತ ಕನ್ನಡ ಮಾತಾಡ್ತಾರೆ. ಅವ್ರು ಹೇಳಿದ್ರು 1 hour ಹಿಂದೆ ಫೋನ್ ಮಾಡಿ ನಾನು ಬಂದು ಮಾಡ್ತಾ ಇರ್ತಾರೆ. ನೋಡಿ ನಮ್ಗೆ ಎಷ್ಟು ಸಪೋರ್ಟ್ ಇದೆ ನ್ಯಾಷನಲ್ ಕಾಲೇಜ್ ಬ್ಯಾಂಗ್ಳೂರ್ ಸೇರಿಸೋಂಗೆ. all due to Dr. Narasimha, the National College and the people who are going. ನನಗೆ ಎಷ್ಟು ಅದೃಷ್ಟ ಅಂದ್ರೆ just standing on the shoulders of the giants. ನಾವೇನು ಕೆಲಸ ಮಾಡಿಲ್ಲ, just standing there, that's all. They are going to there. ಅಂತ ಸಮಯದಲ್ಲಿ ಪ್ರೊಫೆಸರ್ ಆರ್ ನರಸಿಂಹನ ಕೇಳಿದಾಗ ಅವ್ರು ಒಂದು ಸ್ವಲ್ಪ ಮಾಡಕ್ಕೆ ಬರ್ತೀನಿ ನಾವು ಅಂತ ಹೇಳಿ ಆ ಸಬ್ಜೆಕ್ಟ್ ಕೊಟ್ಟು ಇಮೇಲ್ ಕಳಿಸಿ ಬಂದಿದ್ದಾರೆ. ವಂಡರ್ಫುಲ್ ಸಬ್ಜೆಕ್ಟ್. ಆ ಸಬ್ಜೆಕ್ಟ್ ನೀವು 2 ನಿಮಿಷ ಯೋಚನೆ ಮಾಡಿದ್ರೆ ನಿಮ್ಗೆ ಗೊತ್ತಾಗ್ತದೆ ಕಾಣುತ್ತೆ. ನಮ್ಮ ಇಂಡಿಯಾದವ್ರು ಹಾಗಿದ್ರು, ಯಾಕೆ ಮಲ್ಕೊಂಡ್ಬಿಟ್ರು, ಯಾಕೆ ಚಿಕ್ಕೋಗ್ಬಿಟ್ಟು, ಯಾಕೆ ಅಮೆರಿಕಕ್ಕೆ ಹೋಗ್ತಿದ್ರು ಎಲ್ಲ ಹೇಳ್ಕೊಳ್ತಾರೆ. ಅಂತ ಬ್ಯೂಟಿಫುಲ್ ಸಬ್ಜೆಕ್ಟ್. Totally, I'm extremely happy. Again, I extend a very warm welcome to Dr. Narasimha and also Mrs. Narasimha and request him to go ahead with the talk.
It's a pleasure to be here. Been here off and on over the last couple of decades. The efforts Professor Narasimha has portrayed there, I think laughing as he always was. The extraordinary effort he put in to run this science forum program, as Dr. Roddam said, 1 month of talks on a variety of subjects, covering virtually the whole breadth of science, and hopefully inspiring a lot of young people. Not inspiring at least, maybe I hope, explaining to a lot of young people why scientists spend so much time doing something and what actually drives the good. This institution is a great institution, National High School and National College. As the name implies, it was actually a part of our national movement, set up by great thinkers. Set up right from the beginning with the objective of advancing education among all people, run by our own people. And it was a model for educational institutions in Bangalore. Has been a model for a very long time. And this program, as Dr. Roddam said, has been running for 37 years. 7 years. And no one has been missed. So once again, it's a great pleasure to be here and to speak to you about something connected with the 9th century of Bhaskara's birth. All of you will have heard about Bhaskara. Bhaskara II, Bhaskara earlier. The author of Bija+Ganitha, but even more widely known, everybody is the author of Lilavati. Lilavati is a book he wrote with a lot of problems, largely arithmetic. It's a very charming book. A very charming book because you see how the problems are given. I remember the kind of problems we used to solve in school. They were usually, well, there might be tough problems, there might be simple problems, a sort of dull problems. Lilavati's book is full of charming problems. At least the situation, the context, for you to solve those equations is wonderful. And nobody who looks at those problems can fail to admire the attitude that Bhaskara had towards mathematics. Lilavati has also now become symbol, if you want, of an icon of women in mathematics. So the Indian Academy of Sciences, when they produced a book on women scientists, it said Lilavati's daughter, that's what the book was called. So you can see how this tradition maintained over so many centuries, and how it's so valued to us to this day. Well, I will say a little bit about Bhaskara, but not a great deal, because a great Bhaskara scholar is here, and that is Dr. Jawaralal. I'm sorry, Dr. Balchandra. Dr. Balchandra Rao is going to speak on Dr. Bhaskar later this month. Therefore, he knows a great deal more about Bhaskar than I do. So I can give it to him to tell you all the interesting things that Bhaskar did. I will say a few words about it later on. But there is a kind of bigger problem concerning the nation, and one should discuss that place with the legacy and the tradition of national college. The bigger problem associated with science in India in general. We take all of this for so much for granted, but most people don't even think about it very much. I am afraid not even scientists. If you go to any lecture hall in National College, or any other college, not in Bangalore, in India, not even in India, all over the world, you go anywhere. The way that science is taught and the way that science is learned, you hear the same people's names, the same heroes, same principles, same subject. Newton, Maxwell, Gauss, more recently Schrödinger, Planck, Einstein, of course, Dirac. Or if you are in engineering, James Watt, Reynolds, it's the same. You see that over the last 200 years, the science that we do, whether we like it or not, is basically Western science. Science was born in the West and we see. Now, sometimes people go back and you hear a few Greek names. All of us studied geometry. I don't know how geometry textbooks are today. When I went to school and first encountered geometry, they had British textbooks. And Holland Stevens. Holland Stevens. So, then it all came from the Greeks. Geometry was due to Euclid. So we learned Euclid's geometry. And we learned how Euclid did his geometry. And I must say that at that time, although I didn't know what the significance of Euclid was in the history and science of the world, it struck me, as it has struck, I think, most people who first encounter the subject, remarkable. There is this man who on page 1 says, I define these things, and I have these 5 axes. And all the rest of the book is deduced from just these 5 axes, even my definition. All there is. God, how does he do that? And then you go through the theorems, the corollaries, so on. It is actually very difficult. Only much later that you learn the significance of it. You also hear about activities. And the thing that strikes me as I grew, the thing that struck me was, you know, I heard an Indian name. I still remember a small book on geometry that Mr. Narasimha, yes. For the first time, a couple of Indian names appeared in this book, in the footnotes. Never in the body of the book. That's when I first heard the name of the book. First heard the name of Bhaskar. There were these people, but I had no idea what they did. I'm afraid the situation has not changed a great deal. I don't know whether it's very different now. They did something, well, okay, they may have been something interesting, but the subject is really basically European. Sorry, it's just like to get the facts that are right. But then, that's how my interest in the history of science started. I just want to find out how this had happened. Then as time goes on, I learned that it was not always so. And in fact, what is happening now is only about 230 years old. If you have gone 500 years back in India, if you had asked one of the leading mathematicians of the country, say for example, Ganitha, who was from Kerala, about European mathematics, he would have said, European mathematics? I don't know anything about it. Is there anything worth knowing? That's what he would have said. You find that Indian accounts of mathematics of that time, there is no interest to Europeans at all. Not the Greeks, not the other Europeans. So you begin to see all these things, actually change over time. So, this is a question which I might have mentioned on this platform many years ago, but I'll come back to this again. A question which I consider very important. It's something which all Indian scientists, students, anybody who is interested in India should really think about. It's not that Nehru was the first man to ask this question. However, Nehru, who was a Cambridge biochemist, who spent the later part of his career studying Chinese science and technology because he heard little bits about it and was so impressed, asked this question. There have been all these great studies of science, mathematics, technology, medicine and so on, great non-European civilizations, China and India, he says. And how is it? 2 points to this question that he raised is that how is it that these great civilizations, China and India, failed to give rise to distinctively modern science? That's one part. Why did distinctively modern science not come up in India? But there's a second part. While being ahead of Europe for 14 previous centuries, he admitted that for 1400 years, interesting things were happening here. Pascal is in the middle of those 1400 years, so to speak. For 1400 years, things were happening here, not in Europe. How come, however, the science came up in Europe, not in, as he said, not in Patna and Peking, but in Pisa. Why did it happen in Pisa but not in Patna and Peking? Well, that is a very interesting question. It's something which we should all answer to ourselves. And I spent some time after long trying to find out what might have happened. Now, if you read the great men of science in the West, then you begin to find that their idea of Indian science is different from what you read about in our own textbook, including in textbooks in India. They will always see that the Indians did something great at some time. Although the Indians' names don't appear in their textbooks either. But some of them have seen that India made extraordinary contributions to the way that science is being done now. And one of the most interesting of those is Hermann Weyl, the late Hermann Weyl, I should say, who was actually one of the pioneers in the mathematics of quantum mechanics. In 1928, he wrote the first book on the subject of the theory of groups and quantum mechanics. It's not theory of groups, it is an integral part of quantum mechanics. See what he says there. He's a mathematician. He's a mathematician of great reputation, but he also had an interest in history. He said Occidental mathematics, well, Western mathematics, actually broke away from the Greek tradition. That's not the subject, that's not the impression that the books give you at all. There were the Greeks, and there was Newton, Galileo, Copernicus, and so on. In between, there was nothing. That's the impression they give you. Nehru says, in between, things were happening greatly there, in India and China. Our books never tell you that. But here's what he says. In those past centuries, actually, it broke away from the Greek tradition. And followed a course, it seems to originate in India. Well, it came to us partly with additions to the Arabs. What was the new thing in this tradition that came from India? Is that the concept of number appears as logically prior to the concept of geometry. And that is central. Now that is, to the Europeans, that was revolutionary. Why was it revolutionary? Well, for them, mathematics was Euclid. Axioms, theorems, corollaries, and so on. If you look at Indian books, you don't find axioms, corollaries, and theorems. You find number. You find rules about handling number. You find ingenious ways in which these numbers are used, these rules are used, by a variety of things, including for predicting where planets are. But the fundamental thing is, not only that the Indians were very good at handling numbers, but they considered numbers as central. In India, mathematics is what? It's Ganitha. Ganitha is counting, reckoning numbers, and so on. In Europe, for a very long time, the word mathematics is actually very recent. It's only for some 300 or 400 years ago. In Europe, mathematician meant somebody who did geometry. Geometer. They didn't use the word mathematician, they used the word geometry. But 300, 400 years ago, the word mathematics picked up. I talked about it a little bit later. So where did this mathematics come from? They didn't have to use the word mathematics. They used the word mathematics. Because the ideas that came from India about number, about how to handle number, about equations, about a wide variety of other things, can't be called geometry. So they have to find the right word. Now, that is what India did to mathematics. Now, what is mathematics in India? Here is a famous shloka from the Vedanta Jyotisha. Yathashikha Mayurana. It's like Navalim Viratala, Purata, like the crest on the peacocks, like the gem in the cobra school. So stands the science of mathematics, if you want to put it that way, Ganitha, at the top of the knowledge that goes into Vedanta. Has given great prominence in India. Well, Indian numerals are well known. You don't have to talk to you about it. It's been said for everybody knows. I don't think everybody knows that the Indians discovered zero is there. That's not quite right. That's not a good way of putting it. What the Indians did was to make a numeral system in which zero was also a numeral, a base of 10, and found a way by making the value of the digit depend on the position occupied in the number different. Suppose there was a place value system. So with 10 symbols, you could express arbitrarily large numbers. Now for most Indians, this seems natural and they don't even wonder about it. But for the Europeans, this was extraordinary. It was extraordinary till 400 years ago, 500 years ago. Do you know that 600 or 700 years ago, young Europeans used to be told, if you want to learn a great deal more about division, you go to the school in Italy where they do Indo-Arabic mathematics. Okay? That's about some 700 years. They were writing 500 years ago, less than 500 years ago. Said, now you don't have to worry about when you multiply by a number which is single digit of 1,000. 1 or 1,000 doesn't matter. Similarly in division. Why? Because 100 years earlier it didn't matter. So this numeral system traveled quite slowly, as you can see. It is implicit in Aryabhata's book, and it first becomes explicit in the commentary. This is Bhaskara first, not Bhaskara second one. Explicit in Bhaskara's commentary. The first inscription is around 595. And it traveled to the Arabs, the Islamic lands from India. Well, there were parts of the subcontinent which had sometimes Persian rule, sometimes Indian rule, and therefore they were quick to see these ideas from India. Al-Khalidi wrote a book about making calculations using methods from India. Al-Hind, as the name itself says. And there were other books. These books were translated into Latin. And you can see here in 1130, there was a book called Algoritmi di Numero Indorum. Algorithms in Indian numbers, in Indian mathematics. That was a book in Latin. Some of them are translations from the Arabic. And so on. There was Leonardo of Pisa, who wrote a book, very keenly aware that these systems came from India. So you can see how long it took. Centuries. But by Newton's time, these things have changed. Numbers, Indian numerals have become very common. And everybody saw the power of using Indian numerals. And Laplace said in 1840, called it ingenious method, which emerged in India. Profound importance and simplicity. It made a big difference to mathematics, which is true. Legal acceptance has still to wait for a long time. Surprising as it may seem, in the 19th century, There are only legal documents in Germany which would not be accepted if you use these numerals, which you still have to use Roman numerals. So it's taken what, more than 1,000 years for the thing to become universal. But today it's almost one of the few things that are universal in the world. The only language which is universal in the world today is the language of the numbers, which the system was discovered in this country. Finally, this is an interesting picture there, sort of announcing, so to speak, the victory of Indian numerals. That lady standing there at the back is the lady of Indians. It's actually written there. It's as if this artist said, his name is here, right? It's like Ganitha Devi, the goddess of Ganitha, if you want, mathematics, arithmetic. And you see the person on the left of the picture, there's the person on the right. The person on the right is using an abacus. That was the standard method of computing at that time. The person on the left is writing 1, 2, 3, striking things. Exactly as we learned through arithmetic in school. You join primary school. So that's arithmetic. And that lady is looking at the other lady who is doing arithmetic this way, smiling at her. Basically he's saying, this is the method, this one over this other method. That was very difficult. The quarrel that had the debates that had gone on in England for a long time, between the abacus, the people using the abacus, and the algorithm, one was over. And we can say Indian numbers at one. That's about 1500, 500 years ago. Let me say a few words about Pascal. Bharatiya Bijapur, Karnataka really, today's Karnataka, sort of Karnataka, Maharashtra, and that concerned area. That mathematics from his father. Composed a book called the Siddhanta Shiromani, which is a quartet, Leelavati, which I mentioned. And we have the Bija+Ganitha, which is about algebra, Jawaralal about spherical geometry, and this is Siddhanta Shiromani, which is an astronomical work. And he made contributions to several branches of what we today consider different fields, different branches of work. And even engineering. When I was an engineer, therefore, I must tell you what Bhaskara did. Bhaskara was the first person in the world, as far as we know, to introduce the concept of a perpetual motion machine. The machine, which was started to keep on running forever. And he even had an idea about how such a perpetual motion machine may be made. This idea actually traveled to Europe. And the medieval engineers in Europe got this idea from India. And they tried like perpetual motion machines. It took everybody a few hundred years more to realize that perpetual motion machines can't be made. And the science of thermodynamics says that perpetual motion is not possible under a wide variety of conditions. So Bhaskara was actually something more than just a mathematician. Bija+Ganitha he defines as Avyakta Ganitha. Avyakta is unexpressed, not clear, therefore it is numerically unexpressed. So it's basically an unknown variable. It is therefore the mathematics, and even the arithmetic belongs to that way, handling unknown variables. Bija is a seed, and presumably is used to indicate that like a seed has hidden material which is capable of yielding fruits, leaves, branches, trees. This unknown thing here can actually, the problem can be solved by using these things. He wrote Bija+Ganitha, every now and then he keeps saying, the reason I do this is because it makes things very clear. The word Spashta Spotaka clearly throughout the book. It's easy to understand. At one place he even says, I read this for Mandabandis. No, people who don't understand the comments. Precise rules can be followed. He stated rules on how to handle numbers, a set of rules. And then he stated rules about these other things. And you go one step, an algorithm is wise. An algorithm is a set of instructions about how you should make a calculation. That comes from the same Al-Khwarizmi who translated Indian books into Arabic. As he introduced the concept to Europe and the Islamic lands, call it an algorithm. An algorithm came from India. The thing about an algorithm is it gives you steps for making a calculation. The thinking goes into making those steps. But once the thinking is done, steps can be followed mechanically with anybody. And you will get the result you want. Well, now the mechanically is become even more significant because the computer will do it. If you have the algorithm, you don't even need human intervention after that. Now this is extraordinary. It's a big step forward in handling mathematics. It has great power. He says it's a source of joy. He says the algorithm, people who calculate, we get a lot of joy by looking at the algorithms in this book. That was his attitude. And admitting you won't make good operation.
Excuse me, sir.
Well,
I want to ask some questions about the
it's best to do it at the end.
At the end. No problem.
So I will do some operation with numbers including 0, positive, negative, search. So you say positive, negative comes naturally to Indians, but it didn't come naturally to Europe. For a long time, negative numbers were still considered rather mysterious. Well, he made various contributions, and I don't think actually I'll go through this in detail because we will hear about them in Dr. Basak Crosslands. He made the handling of unknown quantities systematic. He handled equations with unknown quantities, including more than one unknown, linear equations, quadratic equations, even equations of higher power. He introduced this famous algorithm, Chakrawala, and so on. He did spherical trigonometry, he used even derivatives. He had some inkling of the theorem which got to be known as Rolle's theorem, which appears as these are part of calculus, but for him it was part still of Ganitha that he was doing. He had many contributions to astronomy, and as I said, it focuses motion machine. Well, that's what Gupta did. I'm sorry, that's what Bhaskara did. Equations, which are the other part, also started in India. There is a manuscript, probably of the 8th century, called the Bakshali manuscript, which was discovered in Peshawar. It has things which look like equations. You have to do with calculating. This was the kind of notation that Indians were familiar with at that time. Unknowns were a dot, a filled dot. It corresponds to x in algebra today. In algebra today. If you have more than one unknown, say x, y, z, for example, in the English, always because the last letters of the alphabet. In India, it was done with colors. Kalaka, Nilaka, Lohita. So, Ka is X, could be X, some unknown variable. Ni is another one, Lo is another one. So, the unknown variables were determined by these syllables. Incidentally, you must remember that it's also like using letters as in English. Ka is 2 letters in English, but one in Sanskrit and in our language. Similarly, one symbol. So one symbol for each unknown. If you had A plus B, in India it was common to write A, B, U for Yutam. So you quite often took the first letter of the operation. But that symbol does not appear between A and B. It appears at the end. It's like A and B added. A, B added. Okay? Similarly, A minus B, A, B subtracted. Strangely, the minus sign is partly of plus. But otherwise, Shaya is reduced by B. When they multiplied, you use Gu, divided, Bhaga. X squared. Ya is actually, I forgot to mention this. Ya power. Ya number, power. Ya was for X, that was also a common. You have only one variable right up into Ya. Wa for square, it is Ya square. So if you wrote yarn wow, you got x squared. How many equations were written this way? So if you had ax squared plus bx plus c plus dx squared plus ax plus f, this is the way you wrote them. This is the way, this is the system which was introduced by Ramagupta to the respondent. Ya va a is a times x squared. Ya b is b times x. Ru c for rupa c is c. And these other things were written down. So the upper row and the lower row are equal. If you got ax plus by equals c, two symbols. You need two symbols for two unknowns, and that's what it was. And I'm sorry, something happened in this slide, and the title and the comment here didn't appear. Now that was something like 6th century, 7th, 8th century maybe. Really what's happening in Europe in the 15th century, okay, some 5-6 centuries later, more like 8th or 9th century. Suppose you have to write x squared minus y squared equals 36. That will be easy from the rules that I described just a minute ago. This is the way one of the pioneers of algebraic notation in Europe did it in the 15th century. Well, to explain it is harder than to explain the Indian notation. But you can also see that it's very similar to the Indian notation. The C, D, and so on, n is minus for subtraction, like triad there. C is the square of something, the square of the first variable, unknown variable, x. The things are very similar. They correspond to the first letters of the operations in Latin. So Indian equations, their idea moved into Europe this way after centuries. I won't spend too much time on this. I think I've actually spoken about this long ago. If you look at trigonometry, it went from India. Trigonometry as we know it today is actually largely Indian. I won't say exclusively Indian, it was there before. But if you take the definition of the sign as you go into trigonometry, that definition came from India. There was a Greek definition. The Greek definition is more complicated and it's unnecessary. The Indian definition is minimal. You only need tables for size between 0 and 90 degrees. Even if you run around 360, you always have to come back with what happens between 0 and 90 degrees. And this tables were made. This is actually a table for size in the algebra here. Believe it or not. Maki, it says sometimes gibberish. You don't understand what it's saying. There's all that's a notation of numbers. They're all 3-digit, 4-digit numbers. And it's very cleverly done. Very cleverly done so that for a sign table, we remember this show like they make a sign table. So that was there. I'm not going to talk to you about that in great detail. See the time is anyhow. Similarly, yeah, this was another method of getting signs. It's actually in today's language. This is actually like integrating this differential equation there. d to y dt squared is a squared theta. I'm sorry, yeah. By y is sine theta, say, example. Now, how do you do it? So, this method comes from the Surya Siddhanta and is discussed in Playfair around 1800. They wrote a paper called the astronomy of the Brahmins. The trigonometry of the Brahmins. And you can see that today we would say this is a difference equation. I assume you do as part of calculus somewhere, first order, second order difference equation. This is a second order differential equation. And this is a second order differential equation. Actually, three variables are involved. yn plus 1, yn and yn minus 1. N is the entry. So if you know yn and yn minus 1, we can get yn plus 1. Second order differential equation is what we expect. So if you are given y0 and y1, namely sin theta at 0 and sin theta at the next step, you can calculate the third step, fourth step, fifth step, and you can make a table. You only have to remember this. You have to remember the first two values. You did not have to make computations on triangles and so on. This was also here. And was unknown in Europe for a long time. And here is what F.R.S said on that system. They, he's also a European actually, but he says they. Maybe the Europeans and the Arabs, neither knew this. Continue to construct their tables by the same methods as Ptolemy, Greek, 200, 150 AD. Till about the end of the 16th century. Okay, that's only 400 years ago. Now the theorem in question, that one is the Hindu rule is found, that was discovered by Bija. That was in Italy. Who was in contact with Indian and Arab mathematics. It was soon after applied in Europe and gave way to the construction of the trigonometrical calendar. All the simplicity is it seems capable of doing. Not far out from Greek, not far out from Greek. As a fundamental reason of known to the incident, the geometers of all those countries. Those countries have geometers. It is greatly preferable to that incident. See that in trigonometry. Well, some fellow in Indian calculus as well. So the Kerala school did a great deal to make this calculus formal and gave a much better basis. But results connected with calculus, or what we would think of as calculus, were known in India very well. Only Indians never gave it a separate name for the subject. They did it as part of algebra, they did it as part of Ganitha and so on. They really thought of it as starting a new subject. When calculus came in Europe, it was a new subject. They all part of who the originator was. In India, the everything has come as part of the kind of mathematics that they normally do. You know, it's another piece of yukti to do it in mathematics. This concept of yukti was very strong in India. Second order interpolation formula, which we call Newton-Stirling in all our books, was known to Brahmagupta. There's something by, it anticipates by 10th century, 1,000 years. 1,000 years, almost 1,000 years before Newton. This formula was known. Newton-Gauss formula was known some 3 centuries earlier in India, in Kerala. The cosine as the derivative of the sine, very old. The Maclaurin series were anticipated by the Keralites and in particular by Bangalore, by something like 3 centuries. Many of these results, which you learn as parts of calculus, known in India, much earlier. You will never find this in any textbook. I think if more Indians knew about this, their attitude to science would change. Madhava was a great man who was the sort of the original leader, the founder of this extraordinary school which came up in Kerala around 1400, 1500, 14th, 15th, 16th century. So all of these roots are there. He did many things. He did what is calculus very much the way it's done in your books today. For example, if you wanted to calculate the area of a sphere, what would you do? You are told to cut it into slices. You say each slice has a small thickness. Okay? You first see what the area is, what slice, then you add them up, and you take the limit. The thickness of the slice goes to 0, and the number of slices becomes infinite. That's exactly what he did. That's what he did around the 14th century, 600 years. Even then, in a symptotic series. But when they do this, Indians don't say, I've discovered a new branch of mathematics or anything. They do it as part of whatever they have to do. Here is an asymptotic sum of the p powers of integers. Sigma I to the power p. Well, if your integers, positive integers, you divide with positive integers. You of course go to infinity. As the number of terms goes to infinity, go to infinity. Quite rapidly actually. Rapidly go to infinity. What happens when very large n? So Markov uses this expression. Okay? Is n to the power p plus 1 by p plus 1. Man, that's an extraordinary result. But what's more, see, if you knew only that, I don't think, as far as I know, I don't think asymptotic series are taught. Are they taught in your bachelor's degree course? I don't know whether they're done or not. Maybe one of the mathematics teachers can tell me. But these results were known long ago. When I was doing mathematics in college, I never heard of asymptotic series. I only heard of convergent series. I And I was told what Cauchy's criterion was, other people's criterion. No, this will fail Cauchy's criterion. It's not convergent at all. It is divergent, as we know, the book is doing. However, it can be approximate. Furthermore, the error as it's defined in Cauchy's definition is infinity actually here. But the error is always smaller than the term you retain. Not only smaller, as a fraction of the term that you retain, it becomes smaller and smaller as a fraction. The percentage error goes down. Numerical error does not go down. But that has made a big difference to mathematics as we do it in the 20th century. And a lot of the fluid dynamics I do would not have been possible without this sort of mathematics. But that was again done centuries ago. So on. Series of trigonometric functions. Now let me get on to the next page. How much time do you have?
You can take your own time.
No, I won't take my own time. So let's look at what some of the great men, how this issue has been skirted around. That's really the interesting thing. Einstein. Well, Einstein said, at the age of 12, I experienced a second wonder in school. In a little book dealing with plain Euclidean geometry, were assertions which, though by no means evident, could nevertheless be proved with such certainty that any doubt appeared to be out of the question. Now, I am not Einstein, but that's exactly what I felt when I saw that. I am sure that's exactly what many students feel when I first come across it. How come the same man seems to be producing all the endless results out of nothing, just by stating those axioms and some definitions? He's arriving at certain conclusions, definite, certain conclusions. In fact, he almost defined for a long time what was meant by certainty. If you did it by that theorem, your results were certain, you could trust them. If you did it by a calculation, no, you could not. You only made one calculation, you don't know it's general. You do it by Euclidean, it is general. It was the central tool in a large part of American mathematics, I mean the Western mathematics for a long time. He also said that the axiom had to be accepted unproved did not disturb me. Okay. That is the key. Now, if you look at old Indian books, it is not that they are unaware that you can do something like this. They don't attribute it to the Greeks or Euclid as far as I was never mentioned. Am I right, Dr. Vasanrao? It was translated only in the 18th century or something in India. But there are things which resemble this in some of the Nyaya texts and so on. They are not particularly recommended, but they also don't like this method. There are fundamental philosophical objections to Euclid's method. People think that the results are certain, but actually the results are not certain, because how do you know what axioms you choose? What you get depends on the axioms you choose. Now when you make a calculation, all of you have heard this thing which computer wallahs say, garbage in, garbage out. Now the Indians said for this kind of logic the same thing, garbage in, garbage out. You make a silly axiom, you get a silly result. So what's great about it? So that method never really caught on in India. Einstein went on. Then, later in his career in college, had the good fortune of hitting upon books which were not too particular in their logical rigor. So this was the departure from Euclid. This actually was the departure triggered by what happened in India, but let me first conclude what he said. The main thoughts stood out clearly and shine out and made the student fascinating. Time axes were reached. As to say what new results which you didn't seem to they would expect. Easily competing with Euclid's geometry. What are those subjects? Analytical geometry, infinite series, the concept of differential integral and integral. He thinks they're all European. Well, they were European in the sense in which they did it. But the Indians knew certainly infinite series and differential integral well before European series. Analytical geometry in some sense, not as clear, but in some sense between the Hindus and the Arabs, subjects were different. But none of this had a truly European origin. All these ideas have roots from India or Arabic matters. He wrote this in 1949. I don't know whether he knew at that time that these actually had roots from outside. 1949, although there were some people who knew something about what was happening, what had happened in India at that time, they were not so clear about the Kerala work. You might well have thought these were also European, but they were not. You can see that the last part of the mathematics. So, now, how it changed, I have not shown you what kind of mathematics penetrated Europe and how it has affected people's views of what was happening in that subject. So I want to repeat once again what I said. In around the year 1500, 500 years ago, one of the names I mentioned there, for example, Gilbert, who was a great mathematician, had been asked about what from Europe they would have liked to know. He probably have said, oh, do the Europeans know something? I don't know what they know. Pretty much, as the Europeans began to say 100 years ago, oh, this is India, what did they know that we don't know now? It was very similar. In fact, around the year 1500, 1600, the Europeans were tackling the same problem as we have tried to tackle in the 20th century. They have said, these guys from the East, the Arab Indians and so on, and the Chinese, seem to know something that we don't know. What is it that they know? How is it that their science and their technology is so advanced that we haven't been able to do it? The man who worried about it first was Francis Bacon. Francis Bacon was a very interesting man. He was partly a philosopher, partly a statesman, politician, and he was very, as a politician, about the bad state of European science and technology compared to what he wanted in the East. He reminds me a bit of Jawaralal Nehru. Jawaralal Nehru was very about this. Francis Bacon was very about 500 years. And he looks at these technologies, you know, he mentions them here. These technologies were printing press, compass, and print and gunpowder. The art of printing gunpowder and the natural gunpowder. And he says, no sect or empire, Ashtar, Ashtar is the also included, seems to have exercised a greater power and influence on human affairs than those mechanical things. None of them were known to the Greeks. That was his problem. Many people there thought that Greece was the fountain of all wisdom. None of them was Greece. All of them came from the East. Greatly very. Silk incident. He was fascinated by silk. And he says, if somebody came and told you that I made this fabric and it comes out of the world, would you believe it? You would say, forget it. But in fact, that's what he did. And so he was very worried. He wanted knowledge to be power. Truth, he said, is usefulness. And he found that the science and technology of his day failed on these criteria. It didn't have knowledge, it didn't have usefulness. So he said, the Greeks, he actually is upset with the Greeks. Far more upset with the Greeks than some Indians might be upset with our ancient past. In fact, the words used about the Greeks are unbelievable. Quacks, he says. Plato, Aristotle, Hippocrates, they're all quacks. Aristotle, that burst of sophist, stupefied by his own unprofitable subtlety. That's what he called it. Composing a manual of madness, can you believe that? That made us slaves of words. Plato, scraps of borrowed information, polished and strung together. Galen, narrow-minded, spinning idle theories. He is sick. He wanted to change the world. That Agrippa is a trivial one. Anyway, he was justified. Because although Euclid is greatly admired, very few people know what happened with the successors of Euclid. They did exactly what I said earlier, lousy axioms, lousy results. They had all kinds of fancy, whimsical axioms and came to fancy, whimsical conclusions. Bacon was aware of what they had done. Therefore, he's scathingly critical of it. So he says they have to do something new. And what he says today, and what he said at that time, sounds not very different from what the Indians have been saying. A new beginning has to be made, he said. Almost exactly as Nehru would have said about 100 years ago, about 70, 80 years ago. And he makes this aphorism number 1. This is number 1 in his book, at that time. Man understands only as much as he has observed the order of nature, in fact, or by inference. That is almost literally the translation of what the Indians used to say. Here, for example, is a sentence from Indic Ideas. He said, how do you get knowledge? Pratyakshana anumana, observation and inference. Those are sections. That is what Bacon said. Those are sections. Not saying he copied it from Indic Ideas. But I think these ideas diffused across Europe. They began to see that there was something beyond axioms, theorems, and so on. That had to do with observation and with inference. The Greeks were not great on observation. Believe it or not, Plato said, flashback, he emphasized it at that point. Plato said, if you are a great astronomer, you really don't need to observe. If you sit in your room, you can reason everything out. That's what he said. Indians will have been shocked. Indic Ideas first learn to observe. First thing, you have to observe. And then try and see what you can do. So, you see how this is. Now, Newton was there in between. So I mentioned my minutes. Newton was there in between. Newton was the man who changed the subject, changed science. Now, he was very familiar with what Bacon had said. He was a great admirer of Bacon. But on the other hand, he could not give up his admiration for the Greeks. At least in his surroundings at that time, Bacon's ideas had not quite caught on. In spite of the fact that Bacon was a very influential man, his ideas had not caught on. So he writes his famous book, Mathematical Principles of Natural Philosophy, that he wrote it in Latin. This is an English translation. It is divided into 3 books. The first 2 books are written as if he was addressing a kind of Euclidist audience. People who think knowledge comes on axioms, laws, and so on. So these are the first 2 pages. I'm showing you the first 2 pages of Newton's book. On the first page are definition. Definition 1, definition 2, definition. On the second page, axiom, where which he means what we call today Newton's laws of motion. 3 laws of motion. Law 1, law 2, law 3 says. That is the first axiom, second axiom, third axiom. And then, the way he does it, is exactly like Euclid. It would be, if you open a page of Euclid, you would see the same thing. See, proposition number 1, and there are these diagrams, construction, argument. You go through the argument. Well, unless you've been used to it when you were a kid, you get a little bit of a headache. To follow that argument, it's not something which is very easy. It can be followed, but it will take care. On the right-hand side, Chandrasekhar, the famous astrophysicist, wrote a commentary on Newton's book. But in this commentary, he doesn't follow Newton's method. He writes, side by side with Newton's theorem, he writes how you would do it today in algebra and calculus. And you can see, if you see what's on the right, it's very clear what he did. If you read through this, you will not know that it is so clear. That's the power of algebra, which Pascal discovered. Pascal propagated. That's the power of the calculus, the kind that the Indians did. You can now see very clearly what was done. But in Chandrasekhar's commentary, you'll never find out that many of these ideas came from actually the ideas, but not the results. See, that's the big thing that I want to mention. Now, a lot of argument about whether Newton actually did it all by algebra and calculus or did it by geometry. Now, one theory is that he was pretty good in algebra and so it was not, and he invented the calculus, so he thought, so the British thought. Leibniz thought he invented calculus in Germany. If there had been a referee who knew his history, he would have said it was neither of you, it came from somewhere else. But he doesn't use calculus, he doesn't use algebra very much. Why did he not use it, although he was a master of the 2 subjects? Now, it looked as if Newton felt as one theory. Geometry had dignity. Algebra did not have dignity. Calculus was very new. This was dignified. This was sort of grammatical, so to speak. them. This was something from abroad, something foreign. They realized that this was something foreign. Why? Because the Greeks had not done it. So you go through his book, you can see how much, that's what Bhaskara said long ago, Spruta. This is Spruta, on the right is Spruta, on the left is not so Spruta. It triggered a revolution actually. And so a lot of things changed. It was not actually, many people say that what Newton did, what the European revolution, scientific revolution did, what mathematicalization of science. That is true in a limited sense. It depends on if you consider the Greeks and the Indians mathematicians or not. For the Europeans, that made some sense because the mathematics began to include algebra. See, earlier, a geometer was a mathematician, but mathematics was not in great use. Then if you also start add algebra to it, you can't call him a geometer. He's obviously not a geometer. He can do analytical geometry, but he can't call it a geometer. So the word mathematics began to be used only some 400 or 500 years ago. In fact, there is an interesting, yes, Descartes thought that he introduced algebra, and he called it barbarous. Algebra for him was barbarous. What did he mean by that? It is from outsiders, it's foreign, it's not ours, he said. It was like saying that when Muslims and all the other people were barbarians as far as they were concerned, and we have learned it from them. Now actually we should not get together with the Arab, and we should say this whole business of mathematicizing Europe was the Hindu-Muslim operation. They learned it from the Muslims immediately because they were the closest neighbors, but the Muslims learned it from Hindus. Incidentally, the Arabs, when they write their books on mathematics, are one of the most generous people who acknowledge where they got it from. The way that they speak about the Hindus is extraordinary. You never hear a European use that kind of language at all. They say, what showers has God, what gifts has God showered on this nation, that they did is extraordinary. And in their history of world science at that time, India was number one. The Hindus were number one. All the others, including the Greeks, came over. Sometimes we should make this point. Hindu-Muslim. So anyway, I can go on like that. And let me stop here. And go back to the quotation I started with from Herman. Why? Now you see that that's exactly what happened. And Herman White was one of a small number of people at that time who acknowledged that. But now the number is slowly growing. More and more people are realizing that this has happened. I think that's probably a good place for me to stop. All the rest of it is really adding to the same program. I want to just go to some conclusions. Just to recap what I said. As far as Indians was concerned, observation and inference were the main thing. Chief instrument of reasoning in India was inference. Anumana. Was Kannada a suspicion about something. And not the technical meaning of the word in Sanskrit. Anumana is inference. You can see that the two are connected in some way, but Anumana is a technical word in Sanskrit meaning inference. And virtually every Indian group, they are very diverse country, but almost all these groups accepted observation, inference, and very often the word of the trustworthy as the primary basis for generating reliable knowledge. That was true across disciplines. It was not just in mathematics. The mathematicians followed the same philosophy as our medical people did. You read Charaka and you read Vivekananda or something like that. You see strong resemblances in what they consider reliable knowledge. Debate was useful, but as a tool, it was suspect. Now is the other word of the other sense of Anumana. They never really completely could reconcile themselves to something which was Tarkar and logic and something. That kind of logic, Indians did not approve. It is useful, but not reliable. That was the basic conclusion. So, and there was this revolution. It was Bacon who changed everything. He used two wide infrared axioms. And this Barbara Sargent got him. Descartes, the infrared axioms came. Bacon, it was his reaction. He still didn't want to give up axioms completely. And that was really what changed European mathematics. And the effect on Europe, it transformed Europe. But I don't have to tell you about the other half of the story. Europe has transformed us. That we know. It's still being transformed, not by Europe, but by the whole world, the rest of the world. Because they took these ideas, put them together in some novel way, and found out how powerful they were. And what the last 200 years have shown, those methods have been more powerful than what our ancestors imagined.